Oh, the last one here, as we saw in the last video, we're kind of locked in and we're just praying to high heaven that the AMP structure here is fairly decent. Okay, and I have no idea if it is. Okay, let's just see what we got here. Okay. Now, I also want to point out something that we may take advantage of in future videos. I don't think I'll do it here necessarily, but you know, with these packet sizes, since they're all even, if you see something interesting, let's say with the 6 lower ones and the 2 upper ones are maybe on their own interesting, then you know, certainly maybe you could go ahead and kind of like deal those off and say that they're a pair that just doesn't seem to fit with the rest of the cards, so you just kind of discard them and then keep what has some really nice structure. Of course, if you subtract 2 cards from 8, which is what we have, you would have 6. Well, that would take you back to the previous video in this series where we showed you lots of ways to look for structure within 6 card packets. Okay, so there will be times when you could like break the packet into 2 sets of 4 or some smaller number and work with it from there. But we promised ourselves that we would we would just deal with this one as is. So we're being forced here. We'll probably look at the other structures for practice, but so we're going to view this as an AMP. Okay, so what do we get here? We get a non-matching. Remember, AMP, you do it in pairs. I should have jogged it on the very first example that I did, and I forgot to do that. So as far as color, no match. These actually match in color and suit. That's kind of nice. No match there in color and no match there in color. Okay, so right now we would have 3 non-matching pairs of cards in color, and then we would have 1 matching pair, but it's a nice one because it actually matches in suit as well. And I suppose one other thing you could point out to just ramp up the surprisal, as we call it, is the fact that, of course, you know, these are matching in suit, so we're going to go with that. But if you notice over here, there's something interesting with this non-matching pair. Look at the card values. What do those add up to? Well, they happen to add up to the same sum as these. So that would be kind of a quirky, fun little characteristic that you would point out that people would think, how in the world could he possibly see that or know that or intuit that? Okay, so in the end, we're going to say there are 3 non-matching pairs of cards. There's 1 that matches in suit, and their values add to 12, as does 1 of the other pairs of non-matching colors. That's weird. Or if that characteristic's a little too weird, what you could do as well, in addition to having 1 pair that matches in suit, you could also just mention that you have 2 non-matching pairs in color, but they're both hearts and clubs. Oh, that's interesting. Hearts and clubs. How could you know that? Okay, you know, as you look at this, just come up with characteristics of interest to you or things that you see. You'll see things in these cards that I won't see as I'm doing this on the fly. Another feature I just spotted that you could use or not use if you would like is the fact that one of our non-matching pairs in colors, the card values are both even. And then we have another non-matching pair in color, and the card values are both even. And within each pair, you'll find a 10 within each pair, and in fact, a red 10. Okay, so, you know, just depending on your short-term memory or just what you think would be interesting to claim that you're seeing in the cards as they're sitting as pairs on the table, and, you know, go ahead with those features. Probably the easiest one of all is to go with what I just mentioned, namely all of the pairs differ in color except for 1 pair, and they're both spades, if you want to remember that at least. Okay, so we could say we have 1 pair of spades, and then we have 3 pairs of opposite colors. And then if you want to also hold on to any one of the 2 or 3 additional features that I've just pointed out, you could do that. And I think if you were to add another feature or 2 to this, I don't think it would be too suspicion generating, okay? Okay, so let's go ahead and move on to the second part of this video here. So what we're going to do, we'll go ahead and just start with the AMP structure, if that's okay. And so we're going to show you some additional shuffles today and different ways to convert from one structure type to another or preserve a given structure type. Now, before we do that, I just realized I failed to do something that I said I would do. Even though here, with this particular packet, we've kind of forced ourselves to work with an AMP structure, right? Because we already had chosen examples for the mirrored 2-cycle. Okay, I just want to point out something. Now, if you don't think the AMP structure is all that amazing for this packet, you're probably right. There is something here. But I want to point out that if you were, and this is the same packet, you can check, if you were to view this same packet as a 2-cycle, you know, we have the freedom to do that in general. We just superficially imposed this on ourselves. Look at what happens. This is the same packet. We get the 10 of hearts and the 2 of hearts. So we have a matching pair of suits. We get the 8 of clubs and the 7 of clubs, another matching pair in suits. We get a 3 and a 10 of opposite color, but then we get a 9 and a 2 of the same suit. So if we had gone with, which we would be free in general to do this, if we had gone with a 2-cycle structure, we could have matched up 3 pairs so that they were of the same suit. And if you look at the nature of the cards, that is the best that can be done with these 8 cards. Because we have 3 spades and only 1 diamond. So going with this as a 2-cycle structure would have been significantly stronger than going with it as an AMP structure, okay? So I just want to point that out because we're kind of artificially limiting ourselves, and the AMP structure for this one is not all that amazing, okay? I mean, it's not too bad. It's just that the 2-cycle structure blows it away, okay? So among these 3 structure types, the chance of finding interesting relationships viewing this packet as either an AMP, a mirrored structure, or 2-cycle is highly, highly likely, okay? So I just didn't want people to feel deflated because I don't think this particular AMP structure is all that amazing, okay? But we would not, in general, have to go with it. Check out the mirrored structure, check out the 2-cycle structure, and you most likely will find something stronger. Okay, so let's go ahead and review some of these shuffles that either convert or preserve structure types. So let's go ahead, we'll bring up our basic list of single shuffles. Okay, so what we're doing here is so this is an AMP, that's how we've chosen to view it. So AK is for alternate Klondike. This is where you Klondike shuffle pairs to the table, but the 4 here is suggesting that we do it into 4 piles, okay? And that ends up being inherent in the name given on the chart there, even if it's not clear. And it's because of the plus J, the judicious stacking, which I can actually show you today. Okay, so what this means then is if you look on the table, this will convert an AMP structure to a 2-cycle structure. So you do a Klondike, okay, into 1 pile, Klondike, another pair into a 2nd pile, 3rd pile, and the last 2 make up a 4th pile. Okay. Now you can stack this from left to right or right to left, and it becomes a 2-cycle. Now this plus J is talking about this judicious stacking, and in particular you can do something that I have called a leapfrog stacking of the piles. Now leapfrog just means from left to right or from right to left. You can jump over the neighbor of that little pile. So you jump over this, the one next to it, and land on the third one. Jump over the third one, land on top of the fourth one, and now you can randomly stack these. Have the spectator tell you how to stack those. Okay, so you either could have done a left to right stacking, a right to left stacking, or a leapfrog stacking from left to right or right to left. Okay, so that's what that plus J means. Now this is a 2-cycle structure relative to the pairs that we noted already. Okay, so once it's a 2-cycle structure, you can do a Charlier shuffle, top to bottom, bottom to top, top to bottom, bottom to top, okay? Or have the spectator just randomly cut the cards before you proceed. That's fine. It will not harm a 2-cycle organization of the cards. It's still a 2-cycle. Okay, now we're going to use the Bessie 2-2 in a way that we haven't yet. So if you go over here to the table, it's line 16. Line 16. So the Bessie 2-2, and then if you come over, you'll notice that 2 cycles can be converted to mirrored packets or mirrored structures as long as you have a multiple of 4 cards, which we do. We have 8. So a Bessie 2-2, how does that work again? This is where you take the top card off twice, in some sense. You take off the top card 1, 2 from the top, 1, 2 from the bottom, 1, 2 from the top, 1, 2 from the bottom. And that's all of the cards being moved from one hand to another. It is now mirrored. Boy, once it's mirrored, you have the stay stack principle. So we can deal this into 2 piles. Now note that we cannot deal it into 3 like we did with the 6 card packets, because 3 divides evenly into 6. It doesn't divide into 8. So we can deal this into 2 piles or 4 piles. Okay, and so I'm suggesting that we just deal into 4 piles. Now it is true that you can do judicious stacking here, and that's even marked over here. So let me show you that really what we're doing is something called the RC shuffle. We're dealing that into a number of piles that divides the packet size. So you're free to have the spectator choose stacking from left to right, stacking right to left, or this leapfrog stacking. So maybe they decide to do the leapfrog stacking from right to left. That would be just fine. And then they're free to tell you how to stack these. Maybe they want this one on top of that one. That's just fine. Now, that's going to preserve a mirrored packet. Okay, so it's still mirrored. And now we're going to convert it to a 2-cycle structure. Okay, and we'll do it by way of the mange. And the mange does that, and we've seen it before in previous videos. The mange will take a mirrored structure to a 2-cycle structure. It comes in 2 varieties, an over-under and an under-over. So we'll go ahead and just do an over-under. So you push off the top card, you go over, under, over, under, over, under, over. Okay, now it is a 2-cycle. Okay, now what we're going to do here is something new we haven't shown you. It's on the larger chart, so let me bring up the larger hidden structures diagram. Okay, so we have a 2-cycle. So we're down, let me get the mouse moving. We're down here, the 2C. Well, up above and to the right, there's this little circle that says CP. C stands for coupled. P stands for piles. Well, what are coupled piles? Well, coupled piles are piles where at each level of the piles, the cards at that level are, quote, related in the way that we've set up at the beginning, okay? So there's a few ways to actually go from a 2-cycle to a pair of coupled piles. the chart tells you that there's a P here. P is for push off 50%. Okay, so one way to do it is just kind of, look at the cards and go, okay, yeah, we have 8 cards. Why don't we set half of them there and half of them here? And then we're going to try something. After all of the mixing that we've done, we're going to see how we do with simply combining the cards at each level. So for example, these are the top cards. So we'll say, hey, you guys are related in that way. You're both the top card. Second one down, you guys are friends. It's almost like living on different levels of an apartment building or something. And the next two, they're friends. And then the people down in the basement, they're friends as well. Okay, so now we got our 4 pairs. Now this will now be a DMP, which we've talked about. DMP means distinct mirrored pairs. So these pairs will be the pairs that we noted at the beginning. Well, I think we really only went with one characteristic. That's all that unusual, I suppose. There's going to be one pair of spades, and then all of the other pairs will be of opposite color, okay? And I still think that's a fairly strong ending, even though, as I mentioned, viewing this original A and P as a 2-cycle is much stronger, I think. Okay, so we know quite a bit still. We know that one of the pairs consists of 2 spades. In fact, if I remember, wasn't it 3 and 9 of spades or something? And then the others are of opposite color. That's what I've sensed. I'm sure I'm just out to lunch here. Let's just check. So are 3 of these of different colors, and 1 is a pair of spades? Oh, those are different colors. Big deal. That could have been by chance. Oh, check this out. We got a couple of spades. And I think I even mumbled under my breath that I thought it was a 3 and a 9. And here it is, a 3 and a 9. Well, we haven't succeeded fully. I claim that these are of different colors. Oh, they are indeed. What about these? Yes, we got all 4 of these correct. I could just feel that 3 of them were in conflict within the pair, and that we had 1 pair of spades, and we did. Ew, that's amazing. I wonder if I could do that sort of thing again. I'm sure I can't. I mean, that had to just be dumb random luck, right? Okay, well, of course, it's not dumb random luck. It's smart use of mathematics is what it is. Okay, so that is the AMP little routine.